We just discussed the operations of adding two matrices and multiplying a matrix with either another matrix, a vector, or a scalar. But some operations of matrices do not involve a second value, whether that be another matrix, vector, or scalar. We have similar functions for scalar numbers, such as negation or complex conjugation. Negation is an operation on a single value, instead of two. For example, if we take the negative of the number -3, it equals 3. Here, the operation of negation was only applied to one number. Similarly, complex conjugation is for a single complex value. For example, the complex conjugate of the complex number 3 plus I is 3 minus I. Again, the conjugate was working on a single complex value, 3 plus I. There are some useful self-operations on matrices as well. One of them uses this idea of complex conjugation. For a matrix A, we define the complex conjugate of A, written as A bar, as the matrix such that each entry of A bar is the complex conjugate of the corresponding entry of A. For example, if we want to compute the complex conjugate of the matrix 1 plus I, 3 minus 2I, 3 minus I, and 4 plus 3I, we take the complex conjugate of each entry. That is the complex conjugate of 1 plus I, the complex conjugate of 3 minus 2I, and so on for each entry. Doing this, we get that the complex conjugate of 1 plus I is 1 minus I, the complex conjugate of 3 minus 2I is 3 plus 2I, the complex conjugate of 3 minus I is 3 plus I, and finally the conjugate of 4 plus 3I is 4 minus 3I, giving us the complex conjugate of our original matrix. Another self-operation of a matrix A is called the transposition, which we denote as A upper T. The entries of the transposed matrix AT can be found by changing the positions of the entries so that the entry Aij moves to the position Ji in the transposed matrix AT. That is, the entry in the ith row and jth column of A becomes the entry in the jth row and ith column of AT. We can also think of this as moving the rows of A to the columns of AT. For example, for the matrix A equals 1, 2, 3, 4, we can compute the transpose of 1, 2, 3, 4 by shifting the first row of A, 1, 2, to be the first column of A transpose. And the second row of A, 3, 4, becomes the second column of A transpose. So we get 1, 2, 3, 4 transpose is 1, 3, 2, 4. We can similarly think of this as moving the columns of A to the rows of A transpose. So we would move the first column of A, 1, 3, to the first row of A transpose. And we would move the second column of A, 2, 4, to the second row of A transpose. Either way we think of it, we get the same matrix 1, 3, 2, 4 as the transpose of the matrix 1, 2, 3, 4.